morning, year 6, and welcome to your science lesson. It's great to see you today, and I hope that you enjoy this lesson. I have fun making these science lessons because I get to do weird and wonderful things in them. So I'm here in the classroom, and I'm giving you a different view of me today. It's one that you probably haven't got to see so close up. Is the bottom half of me, because I've got to get We're going to be talking about forces today and measuring forces. And I want to introduce you to this guy here. This is called a spring scale. And what this does is it's got two graduations here. On one side it's got grams, on the other side it's got newtons. And if you notice the graduations here on the grams, similar digits appear on the Newton side. And from this you're able to deduce that there's a certain relationship between grams and newtons. Now remember, grams is an SI unit for weight, and newtons is the SI unit for force. And this spring scale here, what it does is it brings the two together. It relates the two. It shows us how a weight relates to the force that is being applied to it. Now it's a very simple device. Inside here, I don't know if you can see this clearly, there is a spring. And these springs are specially calibrated to have a certain amount of resistance on them so that they give a true reading across all the different scales that you can buy. Now, if we are talking about mass and the weight of something, remember, mass is how much stuff there is, how much of an object there is, how much matter there is in an object. And weight is how gravity affects this object and how much force gravity is applying as it pulls it down. So instead of guessing what this could be each time we talk about mass, what we actually do is we can use a scale. In this case, it's a simple spring scale, and we hook it onto part of what we want to measure. Just going to stick it in this hole here, and watch the scale. As we let the sellotape holder fall or hang, sorry, I'll just pick you up quickly, we see that a certain force is being applied on the scale. Turn it so that there's no reflection. And if I bounce it up and down, you can see the spring moving in there. So we have got 1,400 grams and 1.4 or 14 newtons. So you can see when the object is resting on the ground, the scale measures no force because the weight is being taken on the surface of the earth. But as I begin to lift against gravity, you see the scale begin to move, but the actual marker is staying in almost the same space. As the spring is extended, and then eventually when the amount of spring force pulling up equals the amount of gravity force pulling down, we're able to lift this weight off the ground. And you can see that we can measure this. Sorry, that came undone. Glad that didn't land on anybody's toes. We can see that this, in terms of weight, weighs 1.4 kgs, and in terms of force, there is a force of 14 newtons pulling down on this sellotape. Now, what is interesting is that while the force of gravity can be measured, there is also the force of friction that we can measure. And that is when an object is lying on the surface of the earth and we are pulling it along the surface of the earth. A certain amount of force exists between the surface of the object being dragged and the surface of the earth, and that is friction. And friction can also be measured, with using exactly the same scale. So what I'm going to do here is I've got this sellotape on the carpet and I'm just going to start pulling it along. So you can see the measurement on the scale comes up and then the sellotape starts to move. But if you look at the measurement on the scale, it's not as much as it was when we were pulling directly against gravity. And you can see as the sellotape catches on the stuff on the carpet, the scale bounces up and down with more force or less force, but it's ranging between 600 newtons to 800 newtons worth of force, or a mass of 6 to 800 grams is being pulled along the ground. This feels like I'm playing with a truck and trailer. So what does this mean? We understand that gravity pulls on objects. And we also understand that the more mass an object has, the more gravity can act on it. And when gravity acts on an object and pulls it very, very close together, it's increasing the surface contact and therefore that friction. Now, yesterday I spoke about, not yesterday, in the other science lesson, I spoke about certain forces that Sir Isaac Newton identified. And he came up with 3 laws that govern force. And we're going to look at one of those forces, the first one today, and it's called inertia. Inertia is when an object that is not moving wants to stay not moving. Or an object that is in motion wants to stay in motion. So that is the reason why when an object is standing still, it requires a force to get it moving. And it will continue to move. It will want to continue to move unless an external force acts on it, and that is friction. In space where there's very little to no friction, especially when you're flying through space, you need very little energy to start something moving. And after that, you can turn off the energy and it'll stay moving at that speed infinitely. It doesn't stop. But here on Earth, we've got friction against the air. You've got friction against the surface of the Earth. So you can feel inertia when you are in a car that is standing still and suddenly the car accelerates. You feel yourself being pushed back into the seat. Now what is actually happening is that the engine is accelerating the car, but you are a loose object within that car. So the car begins to accelerate first, and then obviously because you're attached to the seat pushes against you and causes you to accelerate with the car. So that feeling of you being pushed back into the seat is actually your body wanting to stand still as the car accelerates and pushes you along. And now what happens when the driver of that car suddenly slams on brakes? You feel yourself being thrown forward and the seatbelt catches you. Again, that is inertia. Your body has been put into motion, and the law of inertia says that once you're in motion, you want to continue. Your body, your mass wants to continue in motion. It doesn't want to stop unless an external force acts on it, and that external force is friction. So when the car begins to slow down, your body inside the car wants to keep moving forward unless an external force stops you. And that's your seatbelt if you're wearing it. If you're not wearing your seatbelt and the car suddenly stops, you inside the car will continue moving at whatever speed the car was moving. So if the car is going at 60 kilometers an hour and hits into the back of another car or hits into a tree and stops suddenly, your body under the force of inertia is going to continue traveling. And it's going to go traveling through the windscreen or into the seat in front of you or into the person that's sitting in front of you. The seatbelt is there to stop that inertia, to catch that force of inertia and to stop you continuing traveling. So basically, the whole idea with force and the Newton's first law of motion is that when an object is standing still, it wants to stay standing still. And when an object is in motion, it wants to continue in motion unless an external force acts on it. And I'm going to show you a couple of experiments that demonstrate how inertia behaves. Right, so what I've got set up here is our sellotape again, and I want to show you how inertia works. Remember when we used the spring scale and we dragged it along the floor? It showed us that even though the object was resting on the earth, there was still a force at play, and a force that's there even when an object is not moving. And that force is friction, it's inertia. Right now, if I left this sellotape container alone, I'd come back tomorrow and find it in exactly the same place. It's not going to suddenly start moving of its own accord because it has inertia. Its mass is under a certain force at this point in time. Friction is acting on it. It's not going anywhere unless an external force acts on it. So if there's a very, very strong wind blowing, you might see it start to move. If the table starts to tip over, you might see it start to move. There it goes, got it, okay? Because gravity starts to take over, gravity will overcome that force of friction and it'll start to pull it down off the table. However, so that's the external force. It wants to stay in place. I want to show you what happens when you are able to overcome that force of inertia very, very quickly with a greater force. So you saw on the scale that the spring scale started, it registered a certain amount of force, and then once the force of me pulling equaled the force of friction or the force of gravity, the sellotape started to move with it. So the same can be demonstrated here. I've now put the sellotape on top of this piece of material, and this piece of material it's sort of reducing the amount of friction. But there is inertia at play here. The sellotape does not want to go anywhere unless an external force acts on it. So if I gently pull the material, inertia is going to be demonstrated immediately. The sellotape doesn't want to leave the surface of the material, and it's just going to follow that material around wherever I take it. If I am able to overcome the inertia of the sellotape, that is the force of friction between the sellotape and the material, and I'm able to do this quick enough, you should see the material vanish and the sellotape stay in exactly the same spot. So now I'm not going to pull this slowly, I'm going to pull it very quickly. 1, 2, 3. You've seen magicians do this before. It's not magic, it is simple science. I'm going to do that again. So watch very carefully. Try and spot this object and see if it moves anywhere. I'll even turn it a bit more sideways for you to have a look. Right? 1, 2, 3. It moved very slightly, but very quickly, the force that I was pulling away the material with quickly overcame the friction and the cloth came away. However, this stayed in place, even though friction was not at play. Because I applied a great force to the material, very little of that force was transferred to this object. And so it moved very little, slightly, but it stayed on the table. So I'm going to do a couple more experiments to show how we can help ourselves overcome inertia and overcome friction in order to make our daily lives a little bit easier. Okay, so remember when we had the scale on the floor and when we were pulling it directly against the friction on the floor, we registered between 600 and, check that peak there, 600 to 800 newtons, 6 to 8 newtons or 600 to 800 grams of force. And when we lifted it directly up into the air, we registered 14 newtons or 1,400 grams worth of force. I want you to notice something interesting here. I'm holding this just above head height. Now look at the scale. I'm going to suddenly drop to the floor and I'm going to move the camera at the same rate as the spring scale so they fall together. Watch what happens to the force that's being registered now that we're moving in gravity's direction. Did you see that? As we started to fall, look at the newtons and the grams. Did you see how they reduced? And then I'm going to go the other way now. We're at 14 newtons and I'm going to suddenly accelerate upwards. Did you see how there was a peak? It went all the way up to 20. That just goes to show when we act against gravity or when we act with gravity, we are either reducing our force when we act with gravity, or when we act against gravity, we are increasing the amount of force needed to do work. So in this experiment here, this is something that the ancient Egyptians set up in order to lift those massive blocks up onto the pyramid. Instead of just dragging their object along the floor until they got to the side of the pyramid and then hoisting it straight up to where they needed it and using so much force, they used what is called an incline plane, which is basically a plank or a board that gradually rises against gravity over a certain amount of distance. And if we look at the force meter now, as I drag the sellotape up this incline, you'll see that there is significantly less force required as it goes up. So, oh wait, that's stuck on the sellotape. Is it going to 1,400? No. Is it going up at the same time as it's going forward? Yes. So not only are we doing two forms of work, but we are also creating a machine that is a little bit more efficient. Is there a way that we could make this even more efficient? Okay, and the answer is yes. This is what we now call reducing friction, and we can use, in the wheel of your bicycle that I spoke about yesterday, ball bearings. I'm just going to use these markers because they've got a round profile. So where it was registering between 800 and 1,000 newtons, grams, or 8 to 10 newtons going up this plane, this incline plane, if I had to put a roller underneath this, it's basically acting like a ball bearing. And now I can read this for you. It's only at 6 newtons. I'll put another one under, and we'll keep going up. 6 newtons. Put another one under. Okay, and it fell off there because it got right to the top. Basically, that is showing us now that your newtons, or the force, the amount of work that is required, is reduced when we reduce friction. And we do this by either using ball bearings, we can use oil, we can use soap, we can use wax. There's so many different things that science has come up with that helps us to reduce friction that makes our work better. But if you remember in that first lesson, I said that there are certain times where you actually want there to be a lot more friction. For example, at the brakes of your bicycle. If there wasn't friction there, you're not going to stop when you need to. So I hope that this demonstration helps make sense of the notes that I'm posting also. I'd like you to make your notes in your notebooks. I'd like you to also make note of the experiments that I've demonstrated here. Each one needs a diagram and a clear explanation of what I've been talking about. And I'm also going to post notes about the first law of forces from Isaac Newton. That is, an object that is standing still wants to remain standing still, or an object in motion wants to continue in motion, and that is what we call the force of inertia. So I hope that this lesson has been enjoyable to watch. I've enjoyed making it, and I hope that you guys are able to make clear notes and the understanding that you have for the subject is good. Keep these notes in your notebooks, because when we come back to school, I'll be referring back to these, and you'll hopefully be able to do some of these experiments for yourself, just to consolidate what you've learned in this lesson. And I wouldn't want your notes to be now somewhere on a laptop that's not at school. They need to be in your notebooks for when you come back to school. Okay, have a nice day and enjoy the rest of your morning.